All right, this is the last material for the whole quarter, and so the last stuff that's on the exam. And I'm not sure why we're on this particular page. All right, well, let's go to today's date. There we go. Oh, well, let's also look at exam 3, August 14th. There is outline for the exam. So your normal stuff for the first 10 points, where you've got the stress strain diagram to draw and label some points on, and then answer some questions about the stuff we're talking today, stress concentration and finite element. Those are the two for today. And then maybe some questions about torsion. And then you've got the basic, the one step or not many step problems, and a lot of those are from the older material. Although there's a beam deflection in there, and there's a torsional shear stress, so there are some of the newer ones in there. Then you've got the multi-step problems, and then you've got the harder problems. And so there should be 16 of them, 6 points each, and same layout as before. I don't know if it'll have the 2 possible bonus points on the first 10 question or 10 points or not. It might, I don't know. Normally there's either 106 or 108 points possible, and that's the layout. So it'll look just like the previous 2 tests. On the August 12th date, there's this questionnaire. So far it's about even on who's going to do what. Well, wait a second. That looks different than it did a minute ago. Well, anyway, now it's not even. There's a lot of people wanting to do exam 1 and not exam 2, although that's not what it looked like before. Did I click on the wrong one? I don't know. But anyway, fill that in, and if you're planning on taking one of the exams, just so I have an idea of what you plan to retake. And I think that gets all of that. Trusses, I've gotten, I think, 12 of them sent to the cutter, but 8 of those were this morning, so I doubt he's cut those. 7 or 8 were this morning. So if you don't see your truss somewhere else, it should be in 126 in Bogart over there, right across the hall, just in a bag, whenever he does cut them. And I don't know when he'll plan on cutting those. I think he goes after the next class, so around 2 o'clock, and that's when he starts cutting on them, unless he's cutting some right now. I didn't go check. Let's see, what else? I also I think on the truss testing day, I wrote or put up a report format. It's just a outline, basically, of the different sections that need to be in the report. So that's that, in case you're not sure what to put in there. The report does need to be a little bit after. You have to do most of it before, but turn it in after you test your truss, because one of the very last sections is explaining why, or if, how the experimental stuff was different from what you projected it to be. So it's not going to be exactly the same, or very unlikely that it's exactly the same. So it could just be that the differences are, you had some statistical error in the lab 1 and lab 2 data, and we didn't really account for that. We didn't put tolerances or anything on our prediction, so we gave a prediction of a number, but that number was based on data that had some tolerance in it, some standard deviation, and some uncertainty, and we didn't account for any of that. So it might be that that's the only reason, or it might be that when you put the truss in the testing fixture, that things started to twist, and so now all your calculations being planar based and it's suddenly out of plane, then your calculations don't really model that. So anyway, you have to actually test the truss to write that very last section. You can write you can write all of the other sections before you actually test the truss, though. Let's see. I think that, don't forget to do quiz 5. It's still out there. I'm not sure when it actually closes. It actually closes way late. Actually, that may be I think that's okay. I think the grades are due the next day. let's see what else. I think that's everything, like bookkeeping wise. WebWork's still out there. There's still WebWork problems to do. This is what we're going to talk about today, this finite element method. So that's a well, actually it doesn't have to be computer based. You can actually do finite element by hand, but it gets really cumbersome if you have many elements. So more recently, and recently in the terms of like all of engineering history, computers have taken over the job of doing finite element analysis. So we'll talk about that, and hopefully we'll be able to show one simple example. If you didn't have a computer, then there is another way to get at the same point, and that's with the stress concentration. So we'll start with that, and then we will do the same problem using SolidWorks to do a finite element analysis and compare the results. On the exam, the stress concentrations, the part you can do by hand actually really easily, that is on the, well, did I put it on the exam? Let's check. It's normally on the exam. I'm not certain I put it on here. Let's see. Yes, it's this one right here. So there is one, looks like just one problem that is, and maybe some questions that concerns stress concentration. So that's what we're about to do. I do need that page though to come back. Let's see, because there's a chart. There's these stress concentration factors that you'll have a similar set of charts like this on the exam. They won't have all this writing on them. It'll just be the chart. So it'll look more like, oops, like that. More like that. So this particular chart has lots of little traces on it, and it's got a picture of what it applies to. So each chart applies to a different type of loading. And so you have many of these charts available out there. You'll be limited to, I don't know, there's maybe 5 or 6 different charts on the test. And you only need one of them. So this one's limited to basically a tab, or you've got a wide area that reduces down to a smaller area, and there's an axial force on it. And so this chart will apply in that scenario. So what you do first is you just do what you've always done in this class anyway, and you solve the base problem. At least that's one way to go about it. So let's say that this is what you are given. Let me make sure my units here. I want certain units. All right. So you've got this plate. It has some thickness that we're not concerned about at the moment, but its thickness is into the page. We're looking at it kind of over the top. This will be 4 inches here, and it reduces down to 2 inches over here. And this feature is called a fillet. It's spelled like fillet, but it is fillet. And it's basically a transition so that you don't have a sharp corner there. You know, you could have this shape, right? You could have this. And you have that sharp corner right there. In general, sharp corners in mechanical designs are bad things to have. For one, they're hard to make because a lot of the ways that you make stuff in metal anyway is with round tooling, and so round tooling has a hard time making sharp corners. So you have to have really tiny bits or whatever to make these sharp corners. Plus, sharp corners have high stress concentration. So, you know, we've been calculating basically this kind of average stress in the bulk of the material, but around these sharp corners, there's a really high stress concentration there. And so there's a really high stress there, meaning compared to anywhere else in the material, and so things start to fail, particularly when things are in a fatigue, so they're loaded and unloaded and loaded and unloaded situation. That'll be really bad for them. So what you do instead is you round it off and put this fillet in here. And normally the dimension that you're given is the radius of this fillet. So we're going to say that this fillet has a 0.4 inch radius. And then we'll make this block 1 inch thick, just so it has some, we'll need some thickness to calculate stress. So 1 inch thick. So we will put some force, an axial force on this thing. Let's make that 1,500 pounds. I mean, it's an inch thick piece of, we'll assume this is steel, some kind of 1020 steel. That doesn't really matter for calculating the stress or anything like that. I need that piece of information for my solver on SolidWorks to be able to solve something. It needs to know what material it is, because it's going to solve not just the stress, but also the deflection, you know, how much does it stretch and all this kind of stuff. So it needs to know what material. So for us on this side, on the stress concentration side, it does matter because the stress we calculate needs to be compared to some material properties to see if it's too much stress, but the calculation doesn't care what material is there on this side. So you should be able to tell that the higher stress, based on what we know, and we're just talking axial stress, it's going to be over in this part because it's smaller. So if we take maybe this little free body diagram here, cut it open, if we put 1,500 pounds of axial force here, then the internal force would have to be 1,500 pounds. And we would go in and say that the axial stress equals 1,500 pounds. And the area here, this dimension is 2 inches. You shouldn't write your dimensions on top of the thing. It's just going to be kind of on top of this now. 2 inches, and then it has a thickness 1 inch thick. So 2 inches by 1 inch. And then we can calculate that. That'll just be 1,500 divided by 2, so 750 psi. Let's get this in my calculator. All right, now that is the stress that we've been calculating, just the average stress in this material. If we calculate the stress over here where I drew the red line, it would be a smaller stress because we'd have the same 1,500 pounds internal force, but a larger area, 4 by 1, so it'd be half of that. But we do have this chart, which shows the same kind of scenario. We've got a wide piece that goes down to a narrow piece, and some dimensions on there, radius of the fillet, force P, some W, H, all this stuff. And what we need to do here is first go down to the x-axis, and it tells us, you know, there's this range of 0 to 1, and it's taking the R, the radius of the fillet. If you look up here, R is radius of the fillet, over H. H is right here, so it's the thickness of the tab part, or the width of that tab. So for us, that is R was 0.4 and H was 2. So if I do that, 0.4 divided by 2, I get 0.02. And so that puts me on this line. Then I need to know which one of these traces do I look at. And they're all described by W over H. So W is the larger piece, so 4 inches. So W over H is 4 inches, and H again is 2 inches. So this is 2. So I look for the line that's associated with W over H equals 2, which is this line. And then I just look where they intersect, and they intersect right here. And I read this number 1.8 off of the y-axis. So K right here is the stress concentration factor. And for my setup geometry here, K equals 1.8. And notice all of these K values, they start at 1 and they get larger. And this thing really gets, steep the closer and closer, but basically the smaller the radius gets. So the closer the radius of the fillet gets to be in a sharp corner, the stress concentration kind of shoots off into infinity, and which you don't want. So for us, K is 1.8, and all you do is you take that sigma max equals the sigma average that we just calculated times K. So we take the 750 psi and multiply times our stress concentration factor of 1.8, and we get 750 times 1.8, 1350. So 1350 psi, which is still a small amount of stress for a steel. Remember, the yield strength of steels are in the 30,000 psi range, and we're at 1300 psi. So it's not a lot of stress at all, but it did almost double it. So and this would be a pretty reliable way. And what it does is it says right around this notch, well, not notch, but right around this transition from wide to thin, I have a higher stress than the average stress in the, well, actually where the green line is over here. And it's around, 1400 psi. So much higher stress than in the other parts of the material. So this is a very simple way. These charts are super easy to use. And they all work more or less the same. You find a value on the x-axis that's related to the feature in proportion to some other part, some other piece of the geometry. You find the right trace to use, and then read the stress concentration factor. So they all work basically the same way. And you take that stress concentration factor and just multiply by the stress that you would calculate just the way we've been doing for the past 10 weeks. So they're really easy to use. And they do give you a pretty good estimate of this larger stress. And that's the way, that's totally legitimate. To do this same process, or well, you're actually doing a little bit more, but there is, well, let's go back to here. We need to talk about the finite element process in general. So using a computer and a simulation package, we're going to use SolidWorks. And again, you can do this same process by hand, but you can't have very many elements just because it's too mathematically cumbersome to do by hand when you have a lot of little pieces. But the general idea is that you build your geometry in whatever package, SolidWorks, whatever it is you're using. You build that. Not a good, difficult thing to do. And then the finite obviously means that there is a limited number of elements. And what you do is you take the geometry that you created, and most of the time, if you're just doing this as the first pass or whatever, the package, the software package you're using will automatically generate what's called a mesh. So a mesh is a system of elements. You can, if you know what you're doing, go in and manually create this mesh. Most things do not do that anymore. It's certainly not on the first pass of, you're just trying to get your model to work and everything. Most of the time you go in and automatically generate this mesh. But when there are specific things or it's a really complex geometry, you may need to at least go in and specify some details about the mesh. What we're going to do is there's a slider that says lots of elements or not lots of elements, and that's kind of what we're going to do for our mesh customization. We're not going to delve into this mesh, but what it does is it breaks up your geometry in lots of little pieces. So, maybe it makes all these little triangles in here. And every one of those triangles is a finite element. So it's, it tries to make them more or less uniform, but all thousands or millions of little triangles. Oh, and now it has depth to it, right? So these are probably actually tetrahedrons. So they're like little pyramids or something. And they take up, and instead of one piece that's shaped like a wide section and a narrow section, you have thousands or millions of these little pyramid shapes. There's kind of like pyramid shapes that all fit together, and each one gets solved for the stress and the displacement, the strain, things like that. Every element gets that. And so what you end up with is, the whole thing gets filled up with all these little elements. Each one gets its own solution to what the stress is in that element, and that element affects all its neighbors, and those neighbors affect their neighbors, and so forth. Somewhere you have to have some boundary conditions. Usually in our case, we're going to put that this edge or this face, because it's three-dimensional, this will be our boundary condition. And that this is fixed. Or maybe you create a boundary condition where something is hinged so it can rotate, or whatever. There's lots of different boundary conditions. For us, we'll just glue that edge to the wall. There's no actual wall there, but if it's just floating in space, most finite element solvers can't deal with that. They need something fixed. It's not quite as simple as just putting a force over here and a force over here. They don't like that most of the time. So in this case, we will fix this face over here, and that's just a boundary condition. We'll add a force on this face. So this will be, and I think SolidWorks is going to call this an external load. And we'll define that to be the same, 1,500 pound. You can apply pressures and forces, things like that, to different faces or lines or individual elements or whatever your scenario needs it to do, and you'll do that. So you'll run this simulation. Every one of those little elements will get solved. Ours with this computer, we're not going to do a super high density mesh, so there won't be that many elements. I guess it'll tell us the number and we'll see how many there are, but it'll take 20 seconds maybe to solve it. When I was doing my PhD, I was doing finite element analysis of femurs. So femur fractures, like your big leg bone would fracture, and you have to put it back together with these giant screws and all that. Back then, this is 1998 or 9 or something like that. You had to build all the geometry yourself, put all the mesh elements in yourself, and let the computer crunch on it for a day, and then you get the numbers back, and hopefully you did everything right and you got valid numbers. The same stuff today you could do in a matter of minutes and have the same results. So things definitely have progressed. The thing you don't know is, did the thing that you get out of here make sense? Like, was it the right number? It would be super easy to create the geometry, put some loads on there, and it'd be totally wrong. So there are a couple of things you do to verify that the computer results actually are real and not just, hey, the computer solved the problem and it must be right. One thing is you do the simple case. You simplify it down to something that you can solve, like this. You go to the stress concentration factors, if it's applicable to what you're doing, and get an estimate for, okay, I know that somewhere around 1,300, 1,400 PSI, that would be the maximum stress on this thing. Other things you do is you solve this finite element a bunch of times with different elements numbers. So you might create a graph like this, where on the x-axis over here you have number of elements, and it doesn't matter the number, but you have, like, I don't know, n, and then over here you have 2 times n, and then 3 times n. So you do it with increasingly more and more elements, and you pick some data that you're interested in, usually a stress. So maybe I want the stress at this little notch where I think it's going to be highest, and I plot that. And if it does something like, like this, then that's a good thing. It tells me that, okay, the first one I did is not that good, the next one, but all of these are reporting the same number of, or same value of this stress at this node or whatever, and so it's converging to the same thing. It would be just as good if it did, something like that. What you don't want is it to do something like that, because that says that, well, something's wrong with the model, because I can throw more elements at it and it gets worse and worse and worse and worse. I don't want it to, oscillate out of control. I don't want it to do that. There's at least that makes it internally valid. It doesn't necessarily tell you that the number is correct. It just means that the model is consistent. And then if you compare it to something theoretical, now actually stress concentrations are not theoretical. This chart is empirical. It's just a chart that's generated by a bunch of experiments. But if they start to compare to theoretical, compares with your converged results and all of that, then you kind of get the feeling that you're doing it correctly. When we actually build this model in SolidWorks, you can watch it deform. It'll exaggerate the deformation, and you can look at it, and after a while of doing this type of thing, you'll know if that looks right or not. So if it's deforming the way you expect the real piece would deform. And so there's a lot of, don't just run as many elements as you can and take this data point because it may or may not be good. So normally, now we're not going to do this, but normally you would do some kind of comparison between theoretical results, convergent test results, and get some level of confidence that the model you built is working correctly. So what we will do, let's go into SolidWorks over here. Let's see. My computer may struggle with trying to do all of this at once. So it won't even let me move the window around for some reason. Ooh. Come on. There we go. All right. We're already in a new part. We don't need this thing. Close though. Wow. I don't want that on there at all. Get off. Wow. Where's the... I don't want it pinned. I want it to go away. All right, well, let's see. Let's sketch. No, I really need that to go away. Okay, there we go. It's just really slow. All right. Let's make a rectangle and another rectangle. And we need some, we made this dimension 4 inches. We didn't actually specify this dimension, so we'll make it 4. Just have a square. And then we made this dimension 2 inches. I didn't specify, but let's trim that off. Trim that thing off. This tab should be centered, so let's make it centered. That should, yeah, it won't let me apply that one, but that's okay. Let's make this distance also 4, just to, I don't know, just because. And then let's add a fillet there and there, and we made those 0.4. Oh, hit the wrong thing. Wow, 0.4. Okay, yes, keep that. All right. I think that's all the dimensions we had on there. So let's end the sketch. Let's actually make it into a extrusion. We made it 1 inch thick. Okay. There we go. All right, so we have this model. Normally you save the model. We're not too worried about this model because, other than my computer being slow right now, it doesn't, not that hard to make. All right, so then in SolidWorks, you go into simulation. Now if you haven't used simulation before in SolidWorks, it may not show up here. So you have to, let's see, I don't know. I think it's in tools and maybe add-ins. Let's see if there's add-ins down here. Yeah, add-ins. And it'll go through and look at all the add-ins that you have installed. Normally it doesn't start these because They just take up a bunch of memory that unless you're actually going to use the add-in at the time, they're not giving you any functionality. So it looks like I could probably turn off a lot of these add-ins. Like I don't need the cam add-in most of the time, so I could turn that off. Not even sure what the composer does. But you've got all of these. You actually have a lot of functionality in this version of SolidWorks, and there would be the simulation when you would want to add it in. And so what that would do is it would add this little tab so that you could use simulation. All right, really don't want that to show. All right, so then you go to simulation tab and you want to do a new study. And then you want to do a static study. There's all these other, you have thermal, you can do heat transfer, a fatigue analysis. So if the loading is cyclical, all this kind of stuff. There's even pressure vessel design down there. And so we just want a static one. You could do a 2D simplification. So basically it just takes the 2D geometry. It doesn't care how thick it is. We don't need to do that. It'll be okay just to do static. So we click check. And then it kind of walks you through these steps over here. There is a wizard, I think, somewhere. I don't see it right now. But if you just right click on part 1, you give it a material. I said this was a 1020 steel. It's going to open up, hopefully, a window of materials that I can choose from, or you can design your own if you really wanted to. But I think the combination of recording this and doing SolidWorks at the same time is really causing it to struggle. All right, there's a 1020. We'll apply, close that. It kind of changed the color a little bit, showing that it's got a material assigned to it. We don't need any connections, but sometimes you might want to connect it to a bolt or a spring or a bearing or something like that. We don't need to do that. We're going to actually do a fixture. So we're going to right click and we're going to do a fixed geometry, and we're just going to click this surface. All those little green arrows are saying, if you can't really, you can see they're showing that they're constraining this face in the X, Y, and Z directions. So that's what we want. So now that face won't move X, Y, or Z. And then we need to go to this end over here and right click on external loads, and it's look at all the loads you can add. We just want a force. And we're going to put it on this face. These arrows show that it's a compressive force, so I want to reverse the direction. So I want a tensile one. And I want the US units just because that's what we did our other problem in, and we put 1,500 pounds. So we're going to put 1,500 pounds there, and we're going to add that. So now I have 1,500 pound purple forces, fix this edge, and it's ready to go. I can run this study now. There are options in mesh where I can go in and have some control over how it creates the mesh and everything, but we're just going to take the defaults on that, which are fine for now. So it just meshed it. Now it's doing the solving part, and it's done, and it gives me some reports here. So let's see if this tells me. That doesn't actually tell me. I want to view the mesh. Let's see. Well, here's the we can show it here. So there's all the little tetrahedron type shapes. Let's look at the details on how many it put in there. Well, that's nodes. Elements, it put 7,000 elements in there, 7,074 elements. Got some other data about how these elements are shaped and all that kind of stuff. It's just a standard solid mesh. Element size of almost 1/4 of an inch. So they're kind of big elements, but there are 7,000 in there. Still something you would not want to do by hand. And aspect ratio, if you have really stretched out elements, that's usually bad. So this one tells you what the maximum stretchiness of these elements is. And so you have all this data. I actually want to see, I get by default 3 different results. I get stress, strain, and displacement. This stress says von Mises. We haven't talked about that. That just means it's a combination of stresses in different directions, but that's more or less what we have. So we're going to show that. That's what we've calculated. But we don't want newtons per meter squared. So let's see if we can, let's see, edit definition. and we're going to change it to KSI. Well, PSI, we did earlier in PSI, so we'll do PSI. You can change the scale of what it's deformed. You know, you can kind of, can y'all see? I don't know, I can see the original outline and then this deformed shape. But it's that deformed shape is multiplied by a factor of nearly 5,000. So you can change it to true scale and it won't look deformed at all with this amount of stress. You can set your own scale or just let it do automatic. Mainly, I just wanted to change it to PSI right here. And it says that our maximum stress is where we thought it was. You know, it's right there in that fillet. And it's 1,367 PSI. We calculated 1,350 PSI. I would say those are pretty agreeable results. You know, the 26 or 7 PSI difference is not a big deal. And we also get stress everywhere else. So at this point, you could go in and you can start to optimize your design. You know, you got all these blue areas over here. Maybe you don't even need that geometry. So if you're trying to minimize weight, you can just chop those corners off. And there's actually, I don't know if this version of SolidWorks has geometry optimization in it or not, but there are, once you get past the general design, there are procedures that you can automatically go in and let the computer start chopping away pieces and creating like web-like structures where the material is needed. Now, to make those structures, you have to use some additive manufacturing process or something like that. Normally, you're not going to create that on a subtractive process like a mill or a lathe, but there are other things you could do. The easiest thing here, you know, obviously, you could just chop these corners off pretty much, and you get almost the exact same stress. You might actually lower the stress because this radius might be a little larger. So you can do the design optimization, design verification. You can tell if this part's going to do what you need it to do in the real world, and you have a bigger picture of what's going on in the whole part. Maybe you don't like this high stress concentration, but then you look at it and it's like, well, that's only 1,300 PSI. That agrees with my theoretical results, and I think that's fine for what I need this to do. And so you can do things like that relatively easily. And then once you start really doing finite element analysis, then it becomes a useful tool for design, analysis, all this kind of stuff. On the exam, I'm not obviously going to have you open up SolidWorks and do this. I'm not going to have you do it by hand. You're just going to need to know, let's close this down so my computer can get some resources back. You're just going to need to know basically, you know, mesh, elements, boundary condition, things like that. We just phrases and terms and definitions. So they'll be in the 10-point questions for as far as an exam goes. I believe there is one web work problem that has you do a finite element comparison with the stress concentrations, but I don't even, that may have gotten taken out even, I don't remember. All right, that is all of the material that we're going to cover for the whole quarter. Next thing, Monday, you've got the test redos. Wednesday, you've got the exam 3. Thursday, you've got the truss. So there is still plenty of stuff to do. Quiz 5 is still open. Web work problems are still open. So make sure you don't just quit. There's a lot still to do, but keep up with it and finish out this quarter.